Okay. Today's section. Today we're just covering one section. Sections on binomial coefficients. And then we have a test next week. Okay, so don't forget that we have the test next week. So, what?
We do?
Yes. So this is section 17. Okay. So this section's focused on binomial coefficients, or in short, you can think about it as focusing on just the binomial equation. Binomial equation, we'll introduce that to you. Something that you've seen special cases of over and over and over again. And the way that you've had to work with these things was Pascal's triangle. So when you see an x plus y to the n, then you use the binomial equation to expand this out. And you had to do this over and over again in your algebra classes. You have to do something like figure out what x plus y squared is, right?
Yeah.
And what is it?
X squared plus 2xy.
So you have x squared plus, you can think xy plus, so you can think about yx, or another xy, however you think about it, and then plus your y squared.
Yeah.
Or in other words, x squared plus 2xy plus y squared, right?
Yeah.
Now, if I were to tell you to figure out x plus y cubed,
X cubed.
then you probably would have done squared two of them first. You probably would have split this into x plus y squared times x plus y, right? We already figured out x plus y squared is that thing. So it's just going to be this whole thing. X squared plus 2xy plus y squared times x plus y, right?
Yeah.
And now multiply your x through, multiply your y through, and add it all up. So what's that equal to? When we put an x through to everything, we get x cubed plus 2x squared y plus xy squared. That's multiplying everything in here by x.
Yeah.
Now I'm going to multiply everything in here by the y, and then we're adding them all up. Plus x squared y plus 2xy squared plus y cubed, right? And now combine like terms. How many x cubed terms do we have?
One.
Just one. So 1x cubed plus, how many x squared y terms do we have?
One.
We have 2x squared y's right there, and then x squared y right there, for a total of 3. X squared y plus, how many x y squared terms do we have? We have 1 here and 2 there, so that's 3 x y squared terms, plus y cubed finally. Everyone follow the algebra there? Now, what if I told you to do something like x plus y to the 6? And expand that out. How much of a nightmare does that sound like?
A nightmare.
You have to take that, multiply by x plus y again, and then again, and then again.
Mm-hmm.
That sounds awful. So chances are you were introduced to something called Pascal's triangle to figure out the coefficients of these things. Because you'll notice a nice pattern here. You see that the exponents here is x to the 3. Let me rewrite this out one more way to notice the pattern with the exponents. We could have also, before I say that, what is anything to the 0?
1.
You good with that?
Yeah.
Anything to 0 is 1. Back to exponents in algebra. So, x cubed is the same thing as x cubed times 1. So I can do this as x cubed times 1 plus 3x squared y plus 3xy squared plus x to the 0 y cubed. And you'll notice that the exponents under x decrement down 1. Remember, when it's x by itself, we can think about it as x to the 1, and we can think about that as y to the 1, right? So looking at the exponents on the x, you got 3, 2, 1, 0. On the y's, you got 0, 1, 2, 3. So the x's count down and the y's count up. So it's easy to figure out this part of the term. The hard part is figuring out the numbers that come in front of it. So if I had to write x plus y to the 6, I know that that would be some number of x to the 6, y to the 0, plus some number of x to the 5, y to the 1, plus dot, 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 plus some number of x to the 1, y to the 5, plus some number x to 0, y to the 6. And we just need to figure out the numbers that come in front of all these things. And then we're done. So it's coming up with the numbers that you stick in front of those that's hard. Right? And that's where Pascal's triangle comes in. It's a shortcut to help us calculate those coefficients. Have you both seen Pascal's triangle, you two?
Yeah.
You've seen it before? Let's remind you of it, maybe that'll help. So Pascal's triangle, we start by drawing a 1. Now we imagine that there's an infinite number of zeros to the left and an infinite number of zeros to the right, with a 1 right there, okay? Now, what we do is, to the left of 1, I add up both the numbers directly above it. What's 0 plus 1?
1.
1. To the right, I add up both the numbers above it. What's 1 plus 0? 1. What's 0 plus 0? 0. So now we imagine everywhere we don't write zeros from there on out. Good? Alright, now let's do the next row. What's 1 plus 0? 1. What's 1 plus 1?
2.
What's 1 plus 0? Alright, tell me the next row to write.
1, 3, 3, 1.
Everyone see how we got that? Alright, Debbie, what's the next row?
1, 4, 6, 4.
Alright, Hayden, what's the next row?
1, 5, 10, 5,
No, lost you.
10, 5.
Perfect. And let's see, for x to the 6, we need one more. So that would be 1, 6, 15, 20, 15, 6, 1. And these would be the coefficients. So if I were to expand this thing out, it would be 1, x to the 6, y to the 0, plus 6, x to the 5, y, plus 15, x to the 4, y squared, plus 20, x cubed, y cubed, plus 15 plus 6 plus 1, dot, 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 and you see how to finish it, right?
Yeah.
That's the power of Pascal's triangle. Saves us a ton of algebra. Right? Now, first off, how do we know that this Pascal's triangle thing even works? What does this have to do with these coefficients? That seems completely arbitrary, completely random. Maybe it just happens to work in the first, 10,000 rows. Maybe there comes a row where it doesn't work anymore. How do we know that this actually works? So that's one of the things that we're going to be proving today. And the second thing, as Chandler pointed out when he got here, he even hates Pascal's triangle. Pascal's triangle is a huge shortcut for the algebra, and he's still annoyed. He's saying that's still taking too long. I don't want to have to calculate all these rows because maybe, say I ask you now to expand out x plus y to the 20. He doesn't want to have to write out 20 rows. And maybe I just want to know one term in here. Maybe I just want to know what's the coefficient to the term that has x to the 5, y to the 15 when I expand this out. Maybe I just want to know the number that comes in front of that. You want to write out Pascal's whole triangle just to figure out one little number? That seems annoying. Maybe there's a better way. And there is. And that's what the binomial equation gives us, binomial formula. It helps us calculate these terms. So I'm going to write this out once. I know you don't understand the notation, but I'm going to write it out, and then we'll start making sense of the notation. And we'll use x plus y to the 5. So let's do Pascal's triangle really quick again. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. Now this would be our coefficients. If we were, so this gives me the coefficients when we expand x plus y to the n for some n.
Are you missing any students?
Yes, we're missing Jeremy and Phoenix.
Okay.
Thanks. X plus y to the n, I need to go, if I call this a 0th row, I need to go to the nth row to find the coefficients for when we expand that out. So if we're talking about x plus y to the 5th, then its coefficients can be found on the 5th row. So this is a 0th row. In other words, what's x plus y to the 0?
1.
It's just 1. And so its coefficient is just 1. What's x plus y to the 1?
X plus y.
It's just x plus y. What's the coefficient on the first term?
1.
What's the coefficient on the second term?
1.
And we already did x plus y squared. That's equal to x squared plus 2xy plus y squared. 1, 2, 1.
Okay.
So if we went x plus y to the 5 now, then its coefficients are going to be in numbers right here. 1, 5, 10, 10, 5, 1. You with me?
Yeah.
Okay. So we know that the answer to this, just using Pascal's triangle, or if we had just done all the algebra, is going to be x to the 5 plus,
1 to
what is it, 1, 5, 10, 10, 5, 1?
the. Yeah, you're right.
X to the 4y plus 10x cubed y squared plus 10x squared y cubed plus 5xy to the 4 plus y to the 5. Okay, that's what it would be.
Yeah.
Now, before we prove anything about this formula, I'm just going to write it out once so that you can see it. And then we'll start making sense of that fancy notation. Because in all of this, the only thing that shouldn't make sense to you is that weird notation right there. Outside of that, you should be able to figure out what this thing is saying. So let's figure out what this thing is saying. This thing is saying that x plus y to the n is equal to this thing. It's saying it's equal to the sum from k equals 0 to n, what's n in our case?
5.
5, of 5, remember all our n's we're replacing with 5, 5 choose k, that's how you read that notation, 5 choose k, x to the n, sorry not n, 5, minus k, y to the k, right? That's just, all I did is rewrote this exact formula, plugging in 5 for n. Now let's expand it out. How do we expand this thing? Remember how we do summation notation? We replace all our k's with zeros, and then add it to what we get when we replace all our k's with 1s, then add it to what we get when we replace all our k's with 2,
Yeah.
all the way up to replacing our k with 5.
Yeah.
So if we were to do that, replacing all our k's with zeros, our first term, what's our first term? Tell me what to write.
If k is 0.
It's going to be 5 choose 0. What's x to the 5 minus 0?
X to 5.
Oh, yeah. It's
X to the 5. What's 5 minus 0? Can you do that quick? You have $5, I take none. How many you got?
5.
Alright, and y to the 0 is just still y to the 0. Alright, so that we plugged in 0 for k, now we need to plug in 1 for k. Right? So that is 5 choose 1. What would I get for my x?
4. X
Yeah,
to
X
4.
to
X to the 4. What would I get for my y?
X, y to the
X.
1. Oh, it's
Y to the 1. Right? We were plugging in 1 for k. So I just rewrote that, replacing all my k's with 1s. Now what happens when I replace all my k's with 2s? We get 5 choose 2.
X to the 3.
5 minus 2 is 3.
And y to the 2.
And y to the 2, because we're replacing all our k's with 2s.
Oh, that's way easier.
Plus, then we're going to have 5 choose 3, x squared, y cubed, plus 5 choose 4, x, y to the 4, plus 5 choose 5, y to the 5. And then we're done. We plugged in all the numbers from 0 through 5. You with me?
What about like the,
Coefficients.
yeah.
Right, these weird things. What on earth are they? We'll figure out how to calculate these things and how to make sense of these things. But when it's all said and done, 5 choose 0 is going to be 1. 5 choose 1 is going to be 5. 5 choose 2 is going to be 10.
What about 5 choose 3?
5 choose 3 is also going to be 10.
Yeah.
Well, we'll make sense of those later. But so now you see how this choose notation, this notation right here, this is our coefficient. So now if we can figure out how to calculate those things, make sense of those things, we can figure out the coefficients to all this and we'd be done. And that's the crux of the whole class, trying to understand these things. So that we can understand this formula. And that's why it's called binomial coefficients. This is called the binomial formula. We're talking about the coefficients for all the terms in the binomial formula. And that's where that name comes from. Okay. So, now I'm going to give you a definition for what exactly we mean by this notation. And we're going to come back and connect it to all this stuff in the end. It's going to be a very random, out of blue definition. Here's the definition for it. Let n and k be natural numbers, where k is less than or equal to n. Sorry, I forgot to put that in there. Actually, it can be bigger than n. Doesn't matter. So, I said right. Let n and k be natural numbers. Then n choose k denotes the number of k element subsets of an n element set. Let's get concrete with that. So, let n and k be natural numbers, then n choose k denotes the number of k element subsets of an n element set. So first I need to pick an n. I'm going to pick 5. So I'm going to pick my n equal to 5, or in other words, we're talking about 5 element set. It could be any 5 element set. I'm just going to pick the 5 element set that has the numbers 1 through 5.
Okay.
This could have been any set with 5 things in it. All right. What does 5 choose 0 ask? What is it counting? It is the number of 0 element subsets you can make from a 5 element set. So here's an example of a 5 element set. How many 0 element subsets can you find of that 5 element set?
1.
1. The only 0 element subset of that 5 element set is the empty set.
Yeah.
That's the only one. So 5 choose 0 is 1.
Okay.
Alright? What does 5 choose 1 ask? It says how many 1 element subsets can you create from a 5 element set?
5.
5. How's he getting 5?
Because you can separate all of the elements.
Right, I can have the set just containing 1, or I can have the set just containing 2, or the set just containing 3, or the set just containing 4, or the set just containing 5. Those are my only options for 1 element sets. So I could have had the set 1, 2, 3, 4, and 5. So there's 5 ways that we could do that. Alright? Oh, now it's going to get a bit harder. 5 choose 2. Let's come back to that one. 5 choose 2, 5 choose 3. Those are a bit hard to think about. Let's jump to the end. What about 5 choose 5? How many 5 element subsets can I create from a 5 element set? 1. The whole set itself.
Yeah.
The whole set is the only subset of that set that has the same size as that set. So there's only one way to do it. Okay, what about how many 4 element sets can we make? 5. How does he get 5?
Because you can separate it 5 ways.
When we create a 4 element subset, another way to think about it is we need to choose one to leave behind.
Yeah.
I can do the set that contains everything except 1. I can do the set that contains everything except 2. I can do a set that contains everything except 3, or except 4, or except 5. So it's the complement of all these. So this one was 5 again. Alright, so now what about 5 choose 2? How many 2 element subsets can I create from a 5 element set? That one's hard to think about. We might just have to brute force that one. What can I have? I can have 1, 2, 1, 3, 1, 4, 1, 5, 2, 3, 2, 4, 2, 5, 3, 4, 3, 5, 4, 5. And we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there was 10 of those. Now let's think about 5 choose 3. How many 3 element subsets could I have created from a 5 element set? Similar trick that we already used. When I create a 3 element subset, that's the same as choosing 2 elements to leave behind. So how many?
Oh, yeah, same amount.
10.
Well, yeah, they're obviously 10.
Yeah. I can have the set that contains everything except 1, 2. I can have the set that contains everything except 1, 3.
Oh.
That's what we mean. A one-to-one pairing. The complement of all these sets now. Right? Have we talked about complement before?
Yes.
Okay, everything that's not in this set, but in our initial one. You see that?
Yeah.
And so the answer here is going to be 10. Good? Now notice, crazy coincidence. So we just really calculated 5 choose 0 through 5 choose 5, which are the coefficients we have here. And what did we get? We got 1, 5, 10, 10, 5, 1. Crazy coincidence, right? So let's move on and try and notice some more general patterns now.
Is there any
Oh, go ahead.
Is there any faster way to do the 5 choose 2 and 5 choose 3 other than just?
We will not be trying to think about counting subsets. That is a very hard way to think about it. You want to skip to the da-da-da-da. Okay, here's the da-da-da-da-da.
Okay.
N choose k is equal to n factorial over n minus k factorial times k factorial. That's how you'll calculate it. And so there's a brute force formula. We'll make sense of that. There's the da-da-da-da. All right. But in the meantime, back to this. So that's all well and good for a 5-element set. Now with a 6-element set, what would 6 choose 0 be?
1.
If we had 6 elements in our set, how many 0-element subsets could we make?
1.
Just 1. What if I had 7 elements?
1.
What if I had 100 elements?
1.
Okay, so then n choose 0 is always
1.
wonderful. So we know, at least, that no matter what it is, the first term always has a coefficient of 1, which is nice. We also notice that with Pascal's triangle, the outer edge was always a 1, 1, 1, 1, 1 all the way down. Huh?
I
Yes.
said yes.
Oh, okay. Now, what was 5 choose 1?
5.
5.
That was 5. It was a number of 1-element subsets I could create from a 5-element set, right?
Yeah.
So what would 10 choose 1 be?
10.
What would 100 choose 1 be?
100.
What's n choose 1?
10.
10. Perfect. Before we come to n choose 2, forget about that one for a second. Now let's think about n choose n. So come back up to a concrete example. If I have a set containing 5 elements, how many 5-element subsets can I create from that list?
1.
Or from that set? 1. If I have an n-element set, how many n-element subsets can I create?
1.
Just 1. And then finally, so this is like looking at 5-4. If I have a 5-element set and I take everything but one element, let me say it different. If I have a 5-element set, how many subsets could I make that contain all but one of the elements?
N. Yeah, it should be
It would just be n. You see that? N, and we're choosing n minus one of them to put in a set. So this is n. Try and get you comfortable with why we call this choose notation, and help you get comfortable with why we call it choose. What it's calculating is, when you count the number of subsets you can create from an n-element set, you're counting the number of ways you could choose this many elements from that set. When I say 5 choose 2, it's the same as counting how many ways can I pull 2 things out of a bag containing 5 items. And it's going to be all the 2-element subsets.
Okay.
Does that make sense?
Yeah.
That's why it's called this choose notation. Very natural to think about that way. It's, you have n options, you're going to choose some number of them. If I have n options, how many ways can I choose 2 of those options? If I have n options, how many ways can I choose all n of them? Right? If there's n things in a bag, how many ways can I take everything out of the bag? One way. How many ways can I take everything out of the bag except one thing? N ways. I can leave behind just the first item, or just the second item, or just the third item, etc. Trying to get you comfortable with choose. Because that is really a natural way to think about it. I know we're ultimately going to be coming to a formula, but sometimes you're not really going to use a formula. It's overkill. Sometimes just understanding what it is that we're talking about will make you think about faster. Like poor college algebra students, they memorize this formula with no context in it. And so now when it comes to something simple, like if you told them to calculate something like 5 choose 1, they're going to pull back out the formula. When to you, that's obvious. How many ways can you choose one thing out of an item, a bag containing 5 items? 5. Duh. You don't need to think about that. And it'll also be a sanity check for you down the road when you're like, I I can't really remember exactly what that formula was, but you know some special cases you can try. Because there's some things that's really easy for you to figure out just in your head. So, we'll come to the formula, don't rely on the formula. Try and get intuition for what this choose means. And then the formula will make sense for the rest of your life. Rather than just memorizing the formula, then that's something you have to memorize for the rest of your life. Okay, so now let's try a harder one. N choose 2.
2n.
2n.
It worked with the one above.
Oh, double the previous number. But go back to Pascal's triangle now for a second. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 4.
6.
Thank you. 1, 5, 10, 10, 5, 1. And choose 2 should always be giving you these numbers right here. This is 2 choose 2. This is 3 choose 2. This is 4 choose 2. This is...
No.
No.
Oh, I said it wrong.
Choose 2.
Yeah, you do.
Yeah, sorry. This is choose 0. This is choose 1. Here's choose 2. Choose 2 is the second one. Or the third one. Right? Let me rewrite out Pascal's triangle using our choose notation. 0 choose 0. 1 choose 0. 1 choose 1. 2 choose 0. 2 choose 1. 2 choose 2. You see how the choose 2 is always going to be in the third now? Our next row would be 3 choose 0. 3 choose 1. 3 choose 2. 3 choose 3.
Yeah.
So those numbers right here. 1, 1, 1, 1, 2, 1, 1, 4. Oops. That's good, right?
Yeah, you're on 3 now.
I'm on this one. 1, 3, 3, 1, etc. So the choose 2's now is going to be this diagonal. So this is choose 2, this is choose 2, this is choose 2, this is choose 2. 5 choose 2, 4 choose 2, 3 choose 2, 2 choose 2. It doesn't necessarily double. What's the pattern there?
Plus 2, plus 3, plus 4.
Ah. He sees the pattern. You start with 1, then you add 2 to get that one, then you add 3 to get that one, then you add 4 to get that one. Our next number here would have been 15, which you would have added 5 to get that one.
And then 20. Oh.
No, then 21, then we would have added 6. Perfect. That's exactly right. So let's make sense of that really quick. I think we can erase some of this. I won't write out all the steps of the proof, but walk you through the intuition to make sure that makes sense. So the proof that n choose 2 is equal to 1 plus, just referencing I'm doing this, 1 plus 2 plus 3 plus ... plus n minus 1. So when we were on the row for 7, we add 6 was the last one we added. So it goes up until the next to last one. So there's a pattern you know, it's just from Pascal's triangle. Let's try and make sense of this though, given what we know about n choose 2. Rather than just know some pattern. But that's good that you know some pattern. Okay. So when we came up with all our n element subsets, let me do this again back in the case when we had 5 choose 2. When we were writing out all our 2 element subsets, we kind of did it in a very natural way. We did first, we split it up and we did 1, 2. Let's come at it the way that follows the numbers are. So I'm going to come at it a different way. If I create all the 2 element subsets I can create from a 5 element set, and I want to do it in an organized way. An organized way. First, I'm going to write down all the sets that have 5, the 2 element subsets that have 5 as the smallest element. How many 2 element subsets can I create that have 5 as the smallest thing in there? 5 and something else. Where 5 is the smallest thing in there, if it's a subset of this. I can't do any. There's 0. I can't put another item in there where 5 is the smallest. So don't start with 5, let's start with 4. How many ways can I finish it if 4 is going to be our smallest item? 1. I can do 4, 5. Okay, now how many ways can I do it if 3 is going to be our smallest element?
2, 4, and 5.
Yeah, I can do 3, 4. Or I can do 3, 5. And how many ways if 2 is our smallest element?
3.
3. I can do 2, 3. I can do 2, 4. And I can do 2, 5. Okay, what about if 1's our smallest element?
4.
I can do 1, 2. I can do 1, 3. I can do 1, 4. And I can do 1, 5. And that's it, right? So now let's try to generalize the pattern that we're, notice, hopefully we all noticed. 1, 2, 3, 4. So we said that 5 choose 2 is equal to 1 plus 2 plus 3 plus 4 when we split up our subsets this way. Notice that that's a special case of what we have up there where you plug in 5 for n. 5 choose 2 is equal to 1 plus 2 plus 3 plus 4. Keep going until you get to n minus 1, or 5 minus 1, or 4.
Okay.
So the 4 was counting all the ones that have 1 as the least element. The 3 we're counting all the ones that have 2 as the least element, all the way up to the ones that we're counting all the ones that have 4 as the least element. So now let's do this again. Imagine we have n choose 2. N choose 2. How many 2-element subsets have n as their smallest element? None. I can't do n and something else there and have n the smallest element when we're talking about the numbers 1 through n. The same reason I couldn't start with 5 up here. I had to start with 4. Or in other words, I have to start with n minus 1. I have to start with one smaller than the thing we're talking about. So n minus 1n, this is the only one I can create where n minus 1 is the smallest. How many can I create where n minus 2 is the smallest?
2.
Right, I can have n minus 2
N minus 1.
and n minus 1. Or I can have n minus 2 and n. Perfect. Dot, dot, dot. How many can I have where 1 is the smallest element?
N.
I can have 1 goes with 2. I can have 1 goes with 3.
Wait, what?
Am I saying n?
You're
I can have 1 goes with 2, 1 goes with 3, where 1's the smallest element.
Oh, wait. That
Wait.
would use it in context of n.
Where'd you put n?
Okay. How many can I have where n minus n plus 1 is the smallest element?
N minus n times.
Or 1 is the smallest element? Look, n's just some number. Eventually we're going to get down to 1.
Yeah.
Doesn't matter that we start with 4 here. We eventually, if we go down far enough, get to 1. We can start with 100.
I see what you're saying.
N just allows us to start anywhere.
Okay.
We're going to eventually get down to 1.
Okay.
Okay. So we compare 1 with 2. We compare 1 with
3.
1 with 3. And we compare 1 with dot, dot, dot. We compare 1 with n. Right?
Yes.
And how many items are going to be on the bottom row here?
N.
N minus 1.
N minus 1.
Minus 1.
Not n, n minus 1. Because we never do 1 paired with 1. We do 1 paired with 2, 1 paired with 3, 1 paired with 4, all the way up to 1 paired with n.
Yeah.
Yeah.
Make sense? Same thing up here. There's only 4 here, not 5.
Yeah.
So you'll notice that this counts the number where n minus 1 is the smallest element. This counts the number where n minus 2 is the smallest element. Dot, 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 dot. This counts the number where 1 is the smallest element.
Yeah.
Since this counts all the 2-element subsets, and this by definition is all the 2-element subsets, then they're equal. That's how the counting proof does.
Okay.
That make sense?
Yeah.
So, still kind of a hard way to think about it, even if we know that. So imagine I asked you to do something like, okay, now I want you to figure out what 101 choose 2 is. Oh, well, that's easy. All we have to do is 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus, tell them to stop.
Keep going.
Keep going.
Keep going.
We gotta keep going to what number?
1.
100. That sounds like a nightmare. We want to add up all those numbers.
N minus 1.
No, that sounds awful. So maybe there's an easier way. And there is. So we know that n choose 2 is equal to this thing.
Mhm.
So now what would 2 times n choose 2 equal? It would equal 2 of these, right?
Yes.
It would equal this plus this. So let's write that out. So I want to know what's 1 plus 2 plus dot 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 plus n minus 2 plus n minus 1. And I'm going to add that with itself, right? Did I confuse you because I wrote different terms? I just rewrote this.
Yeah, I know.
Okay, so that is right here. Just rewrote it. Now I'm going to add this to itself in a clever way. N minus 1 plus n minus 2 plus dot 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 plus 2 plus 1. I can flip the order I add those, right? Doesn't matter.
Yeah.
Now I add them all together and what do we get? What's 1 plus n minus 1?
And
N minus 1.
times.
Oh,
It's n.
What is 1 plus
N.
n minus 1
N.
equal to?
N.
N. That's a quick algebra. All right. So that's going to be n plus, what's 2 plus n minus 2? N plus dot 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 plus
And
n plus n. So when we count it twice, notice that we just get a bunch of n's. And how many n's do we get?
N.
n minus 1.
N minus 1 n's,
Oh, right.
right? Because we did all the numbers from 1 to n minus 1, adding them together.
Yeah.
So 2 times n choose 2 is equal to n minus 1 times.
Okay. Oh, okay.
Oh.
Or in other words, n choose 2 is equal to divide both sides by 2,
N minus 1.
n times n minus 1
Over 2.
all over 2. And now you can calculate n choose 2 really quick for any number. What's 100 and 1 choose 2?
100
100 times 101
times
divided by 2.
101.
So we have 101 times 100 divided by 2.
Yeah.
Or in other words, take the 100 divided by 2 is 50 and times it by that, and what do we get? 50050, right? Is that right?
It looks right. So there's 2 zeros of 50 times 10. And then 1 with 50 times 1. Because it doesn't at the same time.
Sometimes wrong in my brain. We're missing. Oh my wow. 101 times 50. Why does that look so weird to me? There we go. 5,050.
Why? There's 2.
There we go.
There's 2 zeros.
I don't know why I just
Oh.
randomly stuck a
That
zero
is
in
right.
there.
Okay.
5,050.
Yeah.
Alright, not sure what happened in my brain in a second. That was weird.
Yeah.
Good?
Yes.
What about like N3? It's the same.
Yeah, notice that now we're in trouble here. Okay, so we figured out n choose 0, n choose 1. Now we got n choose 2. That's this way. But we can also have n choose 3, n choose 4, n choose 5, n choose 6, n choose 7. None of this helps us figure out if I ask you to calculate something like 1, 5, 9, choose 27. Right? So all this work and we figured out what? 5 special cases? Seems like we're taking a long time to get nowhere, right? Don't worry, we're getting somewhere. Okay.
Couldn't you use the same formula, just plug it in for N?
No, that was counting 2-element subsets. That's not necessarily the same thing as counting 3-element subsets. It happened to be the same thing as counting 3-element subsets up here,
Yeah, I know.
but that was a coincidence. Okay, so now, in general, that doesn't help us. So, but now we know some special cases, at least. Now let's do some more special cases. Let's figure out why this 5 choose 3 was the same as 5 choose 2, or why 5 choose 1 was the same as 5 choose 4, or why 5 choose 0 was the same as 5 choose 5. in short, n choose k is always the same as n choose n minus k. Example, 5 choose 2 and 5 choose 3 are the same. So let's make sense of this notation here. Let's actually pick a big complex example first to help us get intuition for this. And then write the formula again. I think you'll get it. Give me an n.
6.
Let's do like 13. And then we'll make this, 5. 13 and 5 is our n and our k.
Okay.
Now 13 choose 5 is the number of 5 element subsets I can create from a 13 element set. Now, for every 5 element subset I create, how many elements do I leave behind? Every time I choose 5 elements to put in my subset, I leave how many behind? 8. So for every 5 element subset, we also have a corresponding 8 element subset.
Yeah.
So there's the same number of 5 element subsets and 8 element subsets. Or in other words, 13 choose 5 is equal to 13 choose 8. Whatever those numbers are, they have to be the same.
Yeah.
Okay.
Back to Pascal's triangle, in short what this was saying is Pascal's triangle has to be symmetric.
Yeah.
Saying that number has to be the same as that, that has to be the same as that, that has to be the same, that has to be the same, that. You have to have the symmetry. And that's why. So now, in general, what is it? In general, it's n choose k is equal to n choose n minus k. If there's n choose k ways that we can take k elements, then there's also that many ways that we can leave n minus k elements behind. If we take k of them, we leave behind n minus k. Does that make sense to everyone? So that's how the proof for this one works. Just the counting proof it does.
Okay.
Saying that this and its that whatever set this is counting the complement of that set. And every set has a unique complement.
Yeah.
Make sense there? Awesome. Okay. So now we come back to that binomial formula that we introduced in the beginning and connect these things with coefficients of the binomial formula. So how are these related to coefficients of the binomial formula? So now we get how these are counting k element subsets of an n element set. We got some intuition for that. What does that have to do with the coefficients of this thing up here when we expand this out? They seem completely unrelated, right? So let's try and make sense of that. And first, let's think about x plus y to the 1. This is equal to x plus y. Right? Now, if I were to ask you, how many one-element lists now, remember, list order matters. How many one-element lists could I make using the letters x's and y?
1.
How many one-element lists could I make using the letters x's and y?
2.
2. I could have the list just containing x and the list just containing y.
Why not x comma y? That
One element list.
Yeah,
One
it's a
element.
1 element.
One element list. So we're talking about parenthesis, you can stick one thing in there and parenthesis. Or parenthesis, you can stick one thing in there and parenthesis. Those are the only one element lists I can make using the letters x's and y.
Yeah.
Okay. Now, I'm going to write out some algebra here. And then I'm going to ask you a completely unrelated question, which is how many two-element lists? First, let's do the algebra. When we expand this out, what do? I can do the x times the x, right? Right? So I could do the x times the x. I could do the x times the y. I could do the y times the x. And I could do the y times the y.
Yeah.
You follow that? Completely unrelated question. How many two-element lists could I make using the letters x's and y?
4.
4. What are those lists?
X, X, X.
I could do xx, xy, yx, yy. Those are all the possible lists. Alright, just to make sure this is sinking in, let's do x plus y cubed now. What's that equal to?
X equals
And just to help visualize here, x plus y cubed is this. Right? And so when we do the xxx, we're saying we take the x from here times the x from here times the x from here. xxx. Now I can do the x from here, the x from here, the y from here.
X equals Y.
Now I can do the x from here, the y from here, the x from here. Plus x, y, y, plus y, x, x, plus y, x, y, plus y, y, x, plus y, y, y. Did I get them all? 1, 2, 3, 4, 5, 6, 7, 8. Perfect, we got them all. Right? That's expanding this out. On a completely unrelated note, how many 3-element lists could I make using the layer x's and y's? 8. How do you know that? When we're creating our list,
2, 3.
we have 2 options for what goes first, 2 options for what goes second, 2 options for what goes third. Or in other words, we have 2 options. Do we take the x or the y? 2 options. Do we take the x or the y? 2 options. Do we take the x or the y? You see that? Wonderful. So you see how if we multiply it out like this, each one of these terms represents one of those lists. Now, that means if I have x plus y to the n, and I were to expand it all out, how many terms would I have that I need to add up?
2 and 2.
I would have 2 to the n. Right? Completely unrelated question. If I have an n element list, how many possible subsets can you create of that n element list?
A lot.
You guys don't remember this? Alright, let's reconnect it. Go back to some math that we already saw, but let's reconnect it. So, pause, flashback to previous class. Flashback to previous class when we were looking at the set 1, 2, 3, 4, 5. Now I said, I want to know what are all the possible subsets I could create of that set? How many possible subsets can I create? I could do the empty set. The set just contain 1, the set just contain 2, the set just contain 3, the set just contain 4, the set just contain 5. I can do the set contain 1, 2, the set contain 1, 3, the set contain 1, 4, the set blah, 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 blah. How many are there?
5, 7.
No, no, no. Now, here's the way we think about it. I'm going to create a word here that has 5 letters. And a word of y's meaning yes, include that element, or x meaning don't include that element. Right? So out of y's and x's, how many possible ways can I do y's and x's here? Give me one combination. You can pick y, y, x, x, y. For yes included, yes, no, no, yes. You with me? Then that would correspond to the subset 1, 2, 5. This would correspond to the subset 1, 2, 5. If I did x, 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 what subset is that? That's the empty set. We're saying don't include any of them. If I did y, 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 how many? What would that be?
It'd be
That would be including all of them.
So it's 2 to the n. Or 2
Right.
to the 5.
You see that for every one of these lists corresponds to one and only one of these subsets. You see that?
Yeah.
And how many of these possible lists are there?
2 to the 5.
2 to the 5.
For this case.
I have 2 options for the 1. When I imagine you're creating your subset. You're creating a bag of candy in a candy store. Just some random bag. And you have 5 options for a candy bar to put in there, yes or no. How many ways could you possibly fill your bag? You have to make 5 decisions. You come to the first candy bar and you decide yes or no, should I put that in there? Right? And you come to your second candy bar and you decide yes or no, should I put that in there? And the third, and the fourth, and the fifth. Every time you putting candy bars in a bag, that's just like creating a set. Does that make sense? So how many ways can you do that? 2 to the 5. you need to make a binary choice 5 times. Yes or no, should we include this? 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 When you answer all 5 of those questions, you created a subset. Good? Okay. So same thing here. We can think about each one of these terms as representing one of the possible 8 subsets of a 3-element set. If we had a 3-element set, the set 1, 2, 3. Then XXX would be which subset? The empty one. YYY would be all of them. XYX would be
2.
the set containing 2. YXY would be
The set containing
1 and 3. So if we do this correspondence, notice that each one of these terms corresponds to one and only one of these possible 3-element, or of the subsets of the 3-element set. Right? So there's going to be 8 of these, or in other words, there's going to be 2 to the 3 of them. So the number of all these terms, when we add them all up, is going to be the number of all possible subsets you can get from an n-element set. That's how many of those terms there's going to be. Now what if we group the terms together? What if we decided we're going to group our terms together by all the ones that have the same number of items in them? You with me? Let's do that grouping. Let's group those terms together by how many. Y means we included the item, X means we didn't, right?
Yeah.
So any bag that has the same number of Y's has the same number of items. So let's group by how many Y's they have. First, let's write all the ones that don't have any Y's. That's just the XXX. There's just one of those. Plus, how many of them had 1 Y?
1, 2.
We had the XXY one, we had the XYX one, and we had the YXX one, right? Plus, and then if we did how many of them had 2 Y's in it,
XYY.
then we would have had the XYY, we would have had the YXY, and we would have had the YYX. And then finally, if we did the ones that had 3 Y's, then that would just be YYY. Right? That's how we can group them. Now in algebra, we call those 3 things there like terms. Right?
Yeah.
And so this would be equal to, now just writing out the algebra, x cubed plus 1, 2, 3. We had 3 that had 2 x's and 1 y. Plus we had 3 that had 1 x and 2 y's. Plus 1 that had 3 y's.
Oh, okay.
So where did that 3 come from?
How many?
That 3 right here was how many 2-element subsets we could create from a 3-element set. That was how many had 2 y's. Oops, I put my parentheses weird here. Sorry about that. These were all the ones that had 2 y's. How many ways can we have just 2 y's? 3. That's what was counting. That's what determined what that coefficient was. Does that make sense?
Yeah.
So that's why these coefficients are these numbers, these n choose k's. Because for some arbitrary element here, so if we were to expand this out, and I were to talk about, let's talk about the term then, let's get a bit arbitrary here. What's the numbers we usually like for n? Let's talk about n equal to 13, okay? So let's pretend that we're talking about n equal to 13. And let's say that I want to know now, when I expanded this out, so we're talking about expanding this out, the coefficient, from k equals 0 to 13 of 13, choose k x, well, we won't say it that way. Forget the formula for a second. Let's just look at it this way. I say when I expand this out, x plus y to the 13 equals da 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 da. I want to know what the term looks like that has, how many y's should we say? 5 y's?
Sure.
Okay, so we'll do 5 y's. Or in other words, we're thinking about the case where k is equal to 5. When we're talking about 5 y's there, how many have 5 y's? Well, if we were to write all these out, expanding out like this, which would be absolutely insane, how many of those would have exactly 5 y's? Let's pick this to be a smaller number just so that we can work with it better. 8. 1, 2, 3, 4, 5, 6, 7, 8. So if it has 5 y's in it, 5 y's showing up in here somewhere, y, we don't know where they show up. Each selection of 5 y's corresponds to, what subset does that correspond to? That corresponds to, we include 1, we don't include 2, we include 3, we include 4, we include 5, we don't include 6, we include 7. Right? When we view it as, when we view each of the terms as talking about a subset of an 8-element set. When we expand it out, just like we did up here, right? So this would be one of the terms that eventually came out in this ink. Sorry, not comma separated like that. It's going to be y times x times y times y times y times x times y. Am I missing an x? Times x. Right? 1, 2, 3, 4, 5, 6, 7, 8. Okay. So if we were to expand this out, this would have been one of the terms in there. Right? Which corresponds to this set. Right? Now we would have also had the other term in there, which would have been something like 1, 2, 3, 4, 5, 1, 2, 3. Which would correspond to the set 1, 2, 3, 4, 5. Here's another 5-element subset of an 8-element set. Here's one, here's one. How many terms like this would we have? We would have however many 5-element subsets there are from an 8-element set.
Okay.
Right?
Yeah.
So that's all that's saying. So that's why the binomial formula works. So when I'm talking about now expanding this out in a concrete case, let's do one that we didn't do before, like 6. X plus y to 6, or x plus y to 6. Then that is going to be how many 0-element subsets we could make.
1.
Right, but just think about it in terms of our counting now. That's how many 0-element subsets we could make where we, sorry, since this is going to be x to the 6, x to the 6 means we didn't include any of the elements, right? So x to the 6 means 0 of 6 were included. Plus 6, 1, that's where we didn't include 5, but we did include 1. Plus, am I overstressing this? Do you guys already get it?
6, 2.
6, 2, which would be
X to the 4.
x to the 4 y squared. Plus dot dot dot, plus finally 6, 2, 6, which is where we just have all y's. We include all of them, right?
So the bottom number is the, what applies to the y, x1?
Yeah, notice that n choose k, y to the k. Remember that the way we thought about it was y is we include the element, x is we don't. So yes, we're going to choose exactly as many as we say yes to. That make sense? Okay. So that's that formula, and that's why it works. So that is why this is giving us the same thing as that binomial formula. You with me? Okay. So, thus far, what should we have made connect so far? 1. You should understand what this notation means. Maybe not how to calculate it in every case, but in theory, how to calculate it. Worst case scenario, if I asked you to calculate 100 choose 5, you could manually write out all the sets and count them. Terrible, but you could in theory do it, right?
Yeah.
So understand what that notation is, and you could, in theory, calculate that problem. Get intuition for what it's counting, and then understand why it shows up here in the binomial formula now. Because when we're counting, the coefficients of those terms are the same as counting the k element subsets you can make from an n element set. Right? You see that? Now, the last thing we need to connect is why does Pascal's triangle work? And then how the formula for this thing, how we come up with an actual formula for it. Let's get to the formula for it. Just because it's really not that hard. Probably should have just started with this. Honestly, it's not that hard to get the formula first, but wanted you to see everything in terms of counting first. So let's jump and get intuition for the formula really quick. Okay, n choose k is supposed to be the number of ways that you can choose k things from a bag containing n. That's an easy way to think about it, right?
Yeah.
So if I've got 5 objects here, 1, 2, 3, 4, 5. Then 5 choose 3 is supposed to equal the number of ways that I can choose 3 objects from the bag. Right? Now let's just make a list of 3 items from the bag. And think about how many ways we can do that. So if I made a list of 3 items from the bag, how many ways can I do that? If I made a list from 3 things out of there, how many options do I have for what goes first in the list? 5. How many options do I have for what goes second in the list? 4. And how many options do I have for what goes third in the list? 3. Or in other words, that's the same as 5 sub 3 notation that you're used to. You with me?
Yeah.
So, that's 5 sub 3, but now notice that so one of the options you could have made is something like 1, 2, 3, right? That could have been your first option, second option, third option. You could have chosen 1, then 2, then 3. Right?
Yeah.
Or you could have chosen 2, then 1, then 3. Are these choices really different?
Yeah.
Yeah, it's a list.
I know that they're lists, but now let's go back to our scenario. I have a bag containing 5 candy bars. I want to say how many ways can Debbie choose out 3 of those candy bars? She has 5 options for her first choice of candy bar, 4 options for her second choice of candy bar, and 3 options for her third choice of candy bar. But then, her choosing a Snickers, then a whatever, is no different than her choosing the whatever, then the Snickers, then the whatever. These are really the same options for her. We don't want those to count differently.
So why don't we use sets? Why do we use lists?
We're coming up with a way to... We are using sets. We're trying to come up with a formula now for calculating this thing. We don't have nice formulas for sets. We have nice formulas for lists. So that's why we're using lists. So I don't want this option to count different from this option, to count different from 3, 2, 1, this option, etc. There's a bunch of options that really aren't different. And so now we can make an equivalence class for this thing. And what's the equivalence class for this thing? It's all the things that have the same numbers. Choosing 5 choose 3, that one was kind of bad. Let's just do 2, because then it makes it easier to write out. 5 choose 2. So 5 choose 2 now. Now she just needs to choose 2 elements from the bag. So she has 5 options for her first candy bar and 4 options for her second, right? So that's 5 sub 2. But now, choosing the candy bar 1, 2, and choosing the candy bar 2, 1, we don't want those to count differently. And so we list out all the possible ways that she can select 2, like 5, 4, or like 1, 2, and 2, 1. And now we create equivalence classes. And we say, actually, the equivalence class on 1, 2, we want to be 1, 2, and 2, 1. We don't want those to count differently. And the equivalence class on 1,5, if she chose a candy bar at 1,5, we want that to be the same as whether it's 1,5 or 5,1. Okay, so first off, how many ways can she choose 2 candy bars when we keep track of the order? That's 5 sub 2, or 5 times 4, right? But now we just want to count the equivalence classes. How big is each equivalence class?
2.
2. So if there's 20 total, and we divide them into classes of 2, how many are there? 10. So 5 choose 2 is 10.
Okay.
Oh,
You with me?
okay.
Let's do it again now, this time with 3. I just don't like 3 because the equivalence classes get bigger. So now if we're talking about 5 choose 3, first off, she has 5 times 4 times 3 options, right? So that's 5 sub 3.
Yeah.
So she could have done 5 times 4 times 3, which is 5 sub 3. But now, each equivalence class, how big is each equivalence class? Because we know that the option 1, 2, 3 is really the equivalence class of this should include 1, 2, 3. It should also include 1, 3, 2. How big is one equivalence class?
2, 3, so 8.
6. 6. Right? Because we just divide by all the different ways that we could order these.
Oh yeah, it is 6.
It's 3 factorial.
Yeah.
Because how many are going to be in this class? How many ways can we arrange the numbers 1, 2, and 3? 6 factorial. Or 3 factorial. So the size of that is going to be 3 factorial. The size of our previous one was 2 factorial. So we took 5 sub 3 and we divided by 3 factorial. Let's do another concrete example before we run off to a formula. Imagine I ask you now, we have 10 candy bars to choose from, and we're going to let her pick 4. She has 10 options for her first candy bar, times 9 options for her second, times 8 for her third, times 7 for her fourth. Right?
10 sub 4.
Sorry, what?
10 sub 4.
You're both saying the same thing. I'm not understanding it.
10 sub 4.
10 sub 4. Yes. Okay. Yes. 10 sub 4. All right. Now, that's how many ways she can select the candy bars, but that was keeping track of order. We don't want order to matter. Right? So how big is one equivalence class going to be? How many ways can you arrange her 4 candy bars?
4 factorial.
4 factorial. So we need to divide by the 4 factorial ways that you can arrange that. So this was the same thing as 10 sub 4 over 4 factorial.
Okay.
In general, if there's n and she's going to choose k, there's n sub k's ways that she can pick them where order matters. And then the equivalence class of the way that you can arrange each of those k things is going to be k factorial.
Okay.
One last piece of the puzzle here. N sub k is n factorial divided by k factorial. Wait. Is that right?
N minus k. Oh.
Yeah, I think that's right. Now, n minus k factorial, thank you. N factorial over n minus k factorial. So, let's get, this is something we already did, but let's reestablish our intuition about it. 10 sub 4 is equal to what? 10 times 9 times 8 times 7, right?
10
But if we think about it as 10 factorial over, what's 10 minus 4? 6 factorial. Notice what this is equal to. 10 factorial is the same as 10 times 9 times 8 times 7 times 6 factorial. Or in other words, times 6 times 5 times 4 times 3 times 2 times 1. All over 6 factorial. 6 factorials go out. You see that? So we already came up with this formula. I think that was on your homework problems, coming up with this formula. So finally, if this is what n sub k is, then we have n sub k over k factorial, or in other words, n factorial over n minus k factorial times k factorial. And so there's our formula for those coefficients. So this is how many ways you can choose k options, k items out of an n element bag, or how many subsets of k you can create from a set with n elements. Make sense? Awesome. So that's your actual formula. And so now with that formula, you can figure out any of these things now, and it's not giving you that much work. Remember how much trouble n sub 2 used to give us? Now we could do something like 27, choose 13, or choose 12, I don't know, real easily. What is it? It's going to be 17 factorial divided by, what's 12, or 17 minus 12? 5 factorial times 12 factorial. There it is. What exact number is that? Who cares? I mean, if you need to figure out exactly what number that is, you can, but...
Is that going to come as an integer?
Yes, it will always be an integer. I think that's one of... That might be the extra credit problem. Is prove that choose notation always gives an integer.
You should prove it.
Or something to that effect. Huh?
You should prove it.
We should prove it?
Yeah.
Or you should try to prove it first. And then we can go from there. But notice that a lot of it is kind of trivial, because the 12 factorial cancels out with a 12 factorial, leaving some higher order terms. And so the crux of the proof is showing that those higher order terms can always be found from these lower order terms. I can't remember if it was a piece to a problem that I had to prove, or if it was the problem I had to prove. But yeah, we have a proof of that.
How long ago did you do this?
Take the class? I don't know. Let's see. 2015-ish? Somewhere around there.
Wow.
Yeah, it's been a little bit. Went to a game over the weekend. I was worried I wouldn't have my voice. All right. So now let's really quick prove that Pascal's triangle works, and then we'll just do one problem that's just for fun, and then we're done for the day. So Pascal's triangle. Now, remember we said, how do we know that the triangle doesn't eventually stop working, right? It happens to work, but so far it just seems like a cute pattern. How do we know it actually works forever? So let's write out Pascal's triangle. And it's 0, 2, 0. Oops. 1, choose 0. 1, choose 1. 2, choose 0. 2, choose 1. 2, choose 2. 3, choose 0. 3, choose 1. 3, choose 2. 3, choose 3. Now, writing the same thing over here, how do we figure this out? 1, 1, 1. We were adding these two numbers to get this number. So this was 1, 2, 1. This was 1, 3, 3, 1. We were assuming that this was always the sum of those two numbers up there. In other words, we were assuming 3, choose 1 is equal to 2, choose 0 plus 2, choose 1. Or 3, choose 2 is equal to 2, choose 1, or 2, choose plus 2, choose 2. I'm not sure what I'm saying. I have the right idea. If we sum those two together, we should get that. If we sum these two together, what should we get?
4 choose 3.
4 choose 3.
2. 4 choose 2.
Is 3.
It's 2.
Oh yeah, you need a 0.
Right? Is it always the case? So is it the case that 3 choose 1 plus 3 choose 2 gives us 4 choose 2? Or in general, this formula, it's called Pascal's identity. Is it the case that n choose k is always equal to n minus 1 choose k minus 1 plus n minus 1 choose k? So if we pick concrete numbers, if we pick 4 for n and 2 for k, here is n minus 1 choose k minus 1. Here is n minus 1 choose k, and here's n choose k.
Oh,
You see how this equaling that sum, in other words, if we kept filling out this triangle, whatever, we'd eventually get down here where we have, on this row, we'd have a n minus 1 and a k minus 1. And then we'd have over here an n minus 1 and a k. And when we filled in the number between them down here, it would be n and k. Because when you go down a row, you increment the top number 1. And then these numbers are on diagonal, on the bottom. So that bottom number has to be the same as that bottom number. You see that? So you see how if we can prove that this plus this is always equal to this, that validates all of Pascal's triangle. Because this is what we're doing over and over again to generate Pascal's triangle. We're using this formula over and over and over again. So if this formula is true, it always works, then Pascal's triangle is valid. And you can use Pascal's triangle. Does that make sense? So all Pascal's triangle reduces to Pascal's identity. So if we can prove this, we're good. Okay, so let's prove that. And it's just a counting proof. What does n sub k count, or n choose k count?
The amount.
The amount
Yeah,
of
that's substitution and then
sets.
Perfect. Let's do a concrete example and then go back to the formula and I think you'll get it. So imagine I wanted to count 10, choose 5. I don't know. We'll pretend that there's 10 students in this class. I may choose 5 of you to get a special award. I may get 5 of you a Snickers bar. I don't know. So here's one way to count it. I'm saying I could also count this. There's another way that I could think about this, as thinking about actually as 9 choose 4 plus 9 choose 5. I can split up and think about it this way. So we know what this is counting. This is counting all the ways that I can give 5 of the 10 people a candy bar. I'm going to call one of the random people in my class Debbie. Right? Now I'm going to say, Debbie, she's my favorite student. And so I'm for sure going to give her a candy bar. And then who's going to get the other 4? I don't know. How many ways could I give the 4 candy bars to the other people? No, 9 choose 4.
Oh.
So initially I have 10 people in the class. I'm going to give 5 candy bars. I have 10. I need to choose 5 to give them a candy bar. If I say Debbie for sure gets one, that's not even a choice. We're just going to give Debbie one. Now how many people are left to decide who to give candy bars to? 9. And I need to choose 4 of them to get a candy bar. On the other hand, if I say Debbie's not even an option, we're not even going to consider her, then now there's only 9 people up for consideration and 5 candy bars to hand out. So this counts all the ways where Debbie is included. This counts all the ways where Debbie is not included. And that counts all the ways. All the ways include, you have the ones where Debbie is included and the ones where Debbie isn't included. This counts where we include Debbie, this counts where we don't. Make sense?
Yeah.
So in general, what do we have? And choose k, we can count first, we can count all the ones where we include our special element. We call one of those random elements Debbie, just because, why not? Just give her a random name. Mark one as special somehow. This counts all the ways where we for sure use that special element. All the subsets that have the special element. Plus, this counts all the ones where we refuse to use that special element. So since I have the special element, I have one less choice now to make, because I'm for sure going to have Debbie. And I have one less option to choose from. And this one, I'm for sure not going to choose Debbie, so I still have k choices to make. So that's how the counting proof for that would go. So this counts the same thing that those two do. All the ones with the special element, all the ones without the special element gives you all of them. Because every subset either does or does not have the special element. Make sense?
Yeah.
Perfect. So that's it for material. Now this is just a fun problem to help you try and absorb some of this. Because you learn these things, then you get some problem and it seems completely unrelated. That's what we're going to do now. Completely unrelated problem that's actually very related. Here's what we're looking at. We're looking at a bird's eye view of some very well laid out city. And these are all the paths you can take on the blocks. Right? With me so far? Now we need to get from point A to point B in the city. How many ways can we get from point A to point B if we require you keep your path as short as possible? So this green, the lighter green, gives us one possible path. How many possible ways can we do this? How many paths can I take from point A to point B if we don't allow any backtracking, basically? You understand the question?
Yeah,
All right, what do you think?
I do not know.
One, you could come all the way on the outside like this, whoop,
Yeah.
and then like that.
That would take forever.
Then you could go whoop, it's the same.
Yeah. I
That
feel-
distance is the same as this distance.
Yeah.
Look,
Okay, actually. Yeah, it's
that
not-
length
it's
plus
not
that
right.
length plus that length plus that length is that. That plus that plus that plus that is that.
Trying to go to triangles or the.
No, no triangles. You can't cut through the buildings. You gotta stay on the road.
So 8 or 2.
So there's two paths,
You
right?
can't just do 2.
Huh?
2.
There's two paths. You can go like this,
But you have to go the other way.
or the green line that I drew here. And those are the only two paths.
No, you can go.
No! There's tons of paths. Okay, so hint. A lot more than 2.
10 squared.
10 squared. Now you're just throwing that out there.
2 to the 10.
2 to the 10.
10 factorial. One of those.
Well, don't just throw out random numbers.
There's 10.
Let's try to think about it.
There's 10 to the x, 10 to the y.
Yeah, see, but you're not even being very clever in thinking about that. Because if there's 10, how many of these do I make?
1, 2, 3, 4, 5, 6, 7, 8, 9.
So there's 10 like that. Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20.
No, it would be.
All right, if I'm standing right here, how many choices do I have?
1 or 2.
I have 2 choices. If we think about, let's do this one block at a time.
Yes.
Because if you're going to go, if I go that way, I at least have to go one block. I can't stop halfway through the block and then go a different direction. Right? So if I'm right here, there's 2 choices I can make. I could either go up or to the right, which puts me right here or right here. So that was 2 so far, right? So I could have gone like that, or I could have gone like that. Now, if I went this way, how many choices do I have? 2. I can go up, or I can go to the right. And here, how many choices do I have?
Wait, what?
If I went this way in the beginning, so I'm right here, how many choices do I have? 2. Which puts me up here or up here. So after 2 moves, how many paths could we have possibly made? 4. I could have gone straight like that, I could have gone like that, I could have gone like that, or I could have gone like that. How many choices am I going to make by the time I get to the end?
2.
10. 10. Well, it was 2 squared to get 4, so 10 squared times 10 squared. Or 10 squared times 2.
I made 2 choices when I was here, right? So my first time I made 2 choices. Now I'm right here or here. With each of those I have how many choices? 2. And that would put me at a bunch of different other locations. And how many options do I have there?
2.
2. How many choices do I have to make to get all the way to the end? Every time I go 1 block.
10 to the end.
How many blocks do I have to travel to get to the end? 20. So just 2 to the 20, right?
Yeah.
Okay, no. That answer's wrong. Shoot.
Dang it.
You seem like a good idea. Why doesn't that answer work?
Because
Well, imagine I chose up, 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 up. Once I get here, how many choices do I have?
1.
One. I have to go to the right. If I'm here, I have to go to the right. So shoot. That seemed like something, and then take us to a dead end.
Just say 2 to 20 minus 2.
Because why not?
There's those two that don't work.
Alright, let's try another way of thinking about this. So, if I go over this way, I'll think about that as going to the right. And if I go up, I'll write that as going up. Then I could write out my directions for the path I took. And so one possible path I take might be go right, right, up, up, right, up, 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 up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
20.
So here's one possible path I could have taken. Right? Marking out this path, I could have gone right, right, up, up, right, and then up to top, and then right. That's what this path says. You with me?
Mm-hmm.
Is that a valid path to get through there?
Yeah.
What if I switch one of these R's with a U? Is it still a valid path?
No. You can't leave the border.
Yeah, it's still a valid path. Let's see. Because we can go up, right, up, which gets us right here, right, and then up how many more times?
1, 2, 3, 4, 5, 6, 7, 8.
8 times. 1, 2, 3, 4, 5, 6, 7, 8. Oh, we went outside the city. That doesn't work. So what do I know about a valid path to get from here to here? How many U's have to show up in it?
10 hours or 10 U's.
There has to be 10 U's. You can only go up 10 times, and you have to go up 10 times. How many R's are there going to be? Yeah, you have to go right 10 times, and you can only go right 10 times. So now, how many possible words can I create with 10 U's and 10 R's?
10.
No. Let's go back to homework problem. Let's see. You were given the word Mississippi.
Yes.
Mississippi. Oh!
It's 20 factorial over.
Thank you.
Over 10 factorial times 10 factorial.
There you go. You got it. And there you go.
Yeah, that makes sense.
Okay, now how does this relate to this
That was it.
Yeah, right there. That would be, well,
So that's how it often goes. A problem that seemed completely unrelated. Coming back to, well, it's the same as counting letters. It's the same as making lists. It's all just counting. Everything's counting. No, not really. But counting comes up a lot. Very natural thing. So that's why you need to become an expert in counting. By the time you finish high school, you should be able to expect a student to count, right?
yeah.
Seems natural.
High school?
High school? Yeah, this is college stuff. You guys are in the deep end. So that's it for today's material. We can spend the rest of class with any homework problems that you have. Test next week. Don't want you guys to do as bad as you on the last one. That's for sure.